Hello everyone. This is my new workshop that I'm going to include in my courses, and this course or this class, whatever you call it, this class has the very high significance related to CFD learning, and especially the topic that is supersonic flow, and it's as I can see that the people here, they don't have the idea that how to simulate the supersonic flows with the possible highest accuracy possible. So they do solve it, but without understanding the different things here. Okay, so I will try to cover these things not in this video but in the coming videos in my courses. So the main point is that this is simulation of the projectile, and it's at the high Mach number, and I will be varying the angle of attacks, and this variation of angle of attack is the interesting thing, or the most important thing is that this is not done manually. What is manually? Manually means that we provide the alpha 4 degrees, so we provide the cos alpha and the sin alpha as angle of attack, and then when we calculate the lift and drag coefficient, we have to provide the those angles again. So I will be using there is a special software that is called the Fluent Arrow. The Fluent Arrow's purpose is that it will simplify these type of simulations, aerodynamic simulations, and it will require the very minimum input. So first case you will solve yourself, then you provide the range of the Mach number, range of the angle of attack, and this will solve the case, and it will provide you the for all the combination of the cases. Okay, for example, if I want to solve for the Mach number, let's say from point 2 to 3.0 with change of point 2. So second Mach number will be the point 4, point 6, point 8, 1, and similarly I want to make the alpha from, let's say, minus 10 to plus 20 or maybe higher, with the change of let's say the 2 degrees. Okay, so now just imagine how many cases these will be. So now you just give this input to the as a panel to the Fluent Arrow. It will take these information and solve for the like a specified convergence criteria or number of iterations, whatever you want to put there, and it saves the data and it will solve the next case. So now imagine that maybe there are the 10 Mach numbers. Okay, there may be 10 angle of attacks. So 10 into 10 is equal to 100. So 100 cases will be solved automatically by the Fluent Arrow. This is the benefit of using the Fluent Arrow as compared to the standard Fluent software that you use for civil simulation. Similarly, I will be teaching you fluid meshing, and also I will teach you ICM CFD hexa, ICM CFD tetraprism, especially for this case. This is the like you can see, it's the rocket, and its model number is it is the IM-7 Sparrow. Okay, so it's a air-to-air missile with a high explosive warhead, and it's a radar guided. So you can see the more details on the Google about this particular object. Okay, and also I'm going to teach you the ICM tetraprism and also the ANSYS meshing, and sometimes I get the request that they want to solve using the hybrid meshing. Hybrid meshing can be inside we have the one region is the tetra meshing with the prism, and outside is the hexa, or maybe hexa inside and outside with the tetra. So there's how to join these two meshes. That's the important point. And then I will also be using CFX, because CFX is also important software, not mentioned here. And the most important thing, you know about the space claim, but the important thing here is that I will be cleaning a dirty STL model into high quality CAD surfaces. Okay, this is the objective aims of this complete course, not completely described here. This is focusing only on the space claim, fluid meshing, fluid solver, and the CFD post, and I will be post processing the data CP plots and other things in the Origin and the Excel. Origin is a very good software, so that's why I thought that I should be teaching you. So this is the overall overview, and this was the geometry that I had. This was like these are the triangles. The STL file contains triangles. Okay, so and then I cleaned the geometry and got these clean surfaces. You can see they are representing exactly same geometry. Okay, I deleted this ring here, but right now it doesn't matter. I think. But if you want to include, you can include it also. So these are parts of the projectile. Okay, the domain size is the very most important thing for any CFD simulation. But problem is that the people don't recognize the difference between the subsonic and the supersonic simulations. So if you are only solving the supersonic flows, then I would suggest that you can actually keep the domain very small. Why so? See, the domain size requirements come from the requirement that when the flow is coming from the inlet and it sees the object here, okay, then the waves, those are sound waves, are reflected back, and the sound waves they are traveling at the Mach number is equal to 1. So now say that our Mach number was 0.6. Okay, so the flow that is going to the body is at a slow speed. Information that is traveling back is at the higher speed. So this will create the disturbance, and the flow field on the inlet will be disturbed. Unless the distance from the body to the inlet is like a very far away. In that case, those waves will be weak and they will not influence the conditions on the inlet. So that's the deciding factor about the like a domain size. So, but in the case of supersonic flows, this information does not travel it does not travel at the higher speed, because the already flow is at the higher Mach number, like a 2 Mach number, 2.5, 3, 3.4, 3.54, like that. Even any Mach number where more than 1 will be the same thing. Okay. So the information will not travel back to the inlet, and it will not be affecting any conditions on the inlet. So domain size can be very small. For example, the length of the missile is like 437, so I call that one as a length L. So the distance here is only 0.5 L, but in case of subsonic flows, I would have been at least keeping the 5 L. And similarly, the downstream side, but downstream side like there is a like wake flow and other things, so that size should be like calculated properly. Now you may ask a question that will it affect the lateral boundaries? Lateral boundaries otherwise, because the geometry is not its length is high, but its diameter and the fins and wings are not very large. It should not be affecting there. But the problem is that there is a shock wave. Okay, and those shock waves may be present, at least they are here and here. So they are going to actually will be the flow features will be moving like this. And problem is that with this thing over there, this will be hitting the boundaries on the sides. So I cannot put the symmetry boundary. Symmetry boundary is very good. It does not produce any boundary layer. The problem is that the flow cannot pass from this boundary. Flow cannot pass from this boundary. Now I can put the like I did it in the some other case. I put the here the pressure outlet, and this solves the problem actually. Okay, non-reflecting pressure outlet solves the problem, but problem is that I don't have the like here is the Sinaga circular domain, so I cannot now it's a straight flow going there, straight line, zero angle of vertex. So if I put the like a pressure outlet, this makes the problem difficult also. There are some difficulties I cannot explain. I don't have the like some physical point of view about explanation, but it does produce the problems. So I cannot use that one either. So the solution is that we have to extend the boundary. So that I came to know after solving the case. Okay, now this is a mesh here. So the mesh here I created is the polyhex core. Polyhex core is like a type of the meshing that will create the polyhedral prisms. Means polyhedral prism means that it will be having the like a traditional prisms. They have the base and the top as a triangle. So in case of the polyhedral prisms, it will be having the 5 or more sides. Okay. So this is about the prisms here. Then In the middle there is the like a polyhedras that are connecting the hex core mesh on the outside. Benefit is that again the polyhedras will be on the outside. So benefit is that we are able to resolve the boundary layer properly with the 10 layers with the smooth transition method applied. First cell was okay, and the Y plus was coming out to be like a 10 from like uh, from 1 to the around 200. That's okay. I wish that I could have like resolved the shock wave with adaptation in this video. This is not an explanation about the any particular tutorial, but this is just overview of the what I am going to teach you. And then I didn't put any density boxes. Density boxes are called density boxes in the ICM CFD. These are the refinement regions. And in case of the ANSYS meshing or fluent meshing, they are now called as the bottom influence or BOI. So these are the volume regions where we can refine the mesh, especially in the back region. The minimum maximum size I kept as a 0.2 and 20, and the stress and gap means that especially the small features like the trailing edge, leading edge of these fins and wings, this was like 3 sets were there, provided that the minimum size is sufficient to allow the 3 elements here. Okay, so this means that if the edge length should be at least 0.6, so size of 0.2 into 3 will be 0.6. Okay, but the thing is that if the size is 0.8, it will not be, it's not going to create the like 4 sets. Okay, these are solid settings which I applied, especially you know about these all things, but I put the high speed numerics activated were activated. And one more suggestion I have is that you should be like using the SA model, and that's a very good for the aerodynamic simulations. Next thing is that I chose the solution steering with supersonic scheme. This is also, you know, I think some of you may know this thing, and this is very good for very fast solution convergence. But this time in the 2024 release 2, we have a new feature that is called the linear ramp up. So it will gradually and linearly and continuously will be increasing the current number. So I chose a maximum limit value as the 50 and minimum was the 1. It started from the 1 and then it went to the 50. So these are boundary conditions, and non-reflecting boundary condition was used at the outlet. Operating pressure was 0. The inlet pressure and outlet pressure were set at the 101, 325 as we do with any compressible simulation. This is a compressible viscous simulation. Okay. So the results were like were disturbed. You can see here. This is the case when I switched from like a symmetry to the pressure outlet. Symmetry had the problem that it was not able to resolve the boundary, the shock wave. It was having the reflections there. Then I switched to the pressure outlet, but pressure outlet again even it worsened the situation as compared to symmetry condition. And also you can see distance from the body to the outlet is also very small. But if you observe it, there is no disturbance on the from like a body to the inlet. So the new domain was created. This time the inlet was fixed one as a 0.5 L, but the outlet like from the only 0.57, it increased to the 5 times almost 3.5, and the height and the width were the 914 millimeter, which is 2 L, so means 1 L on the top and 1 L on the bottom. And similarly the right and left side there also one equal to the 1 L, that is equal to the 437 millimeter approximately. This is approximately 2 L. Okay, so then the density boxes were included. One was just covering the body, and its diameter was 120 millimeters, and it almost started from the like your nose cone and ended to the like some portion after the outlet, the body of the end of the body. The second density box started before the like ending of the second density box or body of influence, and its length was around 1.22 L and diameter varies there to cover the wake region. Although I have seen that thing later that there's not much we have the wake region as we do see in case of the wings, but I expect that at higher angle of attacks we will be having the wake region on the different direction. So this is like okay for to cater for those situations. So here you can see the difference between the domain size, the first domain and second domain, and there is a huge difference in the lateral boundaries and outlet boundary. The mesh, this time the mesh size remains almost similar, it reduced even from 2 million to 1.97 million. Even we kept the 10 prism layers, smooth transition. First cell height was decided by the software itself. You can see the prism layers at the cone and at the outlet section. And there's a very refined mesh here, that is because of the density box. Okay, and also we have the refined mesh around the body, that is again because of the density box. So two density boxes were used, and the sizes I put there, that's definitely after the I put the some small size like 0.5, then 1, then 2. It was making the very fine mesh. Then I come up with a 4 and then 10. I would recommend that the second size may be reduced to the maybe like a 8 or maybe 7. The minimum maximum size were 0.2 and the 50. Why 50? Because domain size now increased, so there is no point of having the a 20 size there. So this much, even this I think this is a fine mesh. So but at least you should have some cells, so I put the 50 here. Cells in gap were 2 and polyhedral were same. This time the number of cells in the gap reduced from the 3 to the 2. Okay, because I found that this does not make any difference at all. Okay, after that I ran the simulations, and you can see the domain size difference here, and especially outlet was not a problem because we have the reflection boundary conditions here, but we had a problem in the over here. So I think that the domain size on the lateral boundaries, this my size would be enough. Okay, would be enough. That is, I think that we have the 2L, so 3L will also 1.5L will be also okay. But that is like a very fine tuning of the domain size. That is not necessary actually. But if you want, I'm just giving you idea. The results are here. This is the density contours. You can see the static pressure contours, again the same behavior you can see here. The Mach number contours, we have the shock wave, and it's oblique shock, and because of the cone angle, and it's not a very strong shock wave here, and also angle is very small. Okay, and we have the some acceleration on the when the fluid exiting from the missile. The Y plus values, maximum value were going up to the 188 for the case of the Mach number 2.5 and 0 angle of attack. Path lines on the body, the vector plots. Okay, now we have some discussion about the forces in the rocket. So there are the two things here that is very important. Center of gravity, because the missile will be going through the different phases, and the center of pressure. Center of pressure will always be behind the center of gravity for the stability reasons. Now there are two forces that you know very well. The lift is always normal to the direction of the wind, and the drag is same direction as the direction of the wind but in the opposite direction. Okay, but the normal force and the axial force, they will be the fixed ones. Means that normal force will always be 90 degrees to the axis of the missile, and the axial force will be parallel to your axis. So they will remain there, and they have some significance, especially in case of when we are going to fire the missile. At that time, the axial forces plays an important role there. Okay, this is the definition again on the aerofoil about the different type of forces. There is a discussion about them here, some discussion more here. Formulas about the drag, lift, axial force and normal force, and then the results. So results we have at angle of attack 0 and 2.5 Mach. CD and CA, which are same in this case, and angle of attack 0. So its value is the 0.0137 and CL is the minus 0.0014. One more important thing is that in the aircraft we actually go with the main aerodynamic card and the projected area, but in this case, in the case of missile, it is about the reference length is the diameter. Okay, this circle, because this is the reference area and the length. Its diameter is D. So its reference length is diameter and the reference area, A reference, is pi by 4 D square. Okay, so you can see the drag is 0.0137 and for Mach number 3 drag is 0.018 and it is like a confirming to the already done simulations that at the low Mach number the drag is very high, then it reduces to the very lowest possible value at transonic condition and again it will start to increase. So same thing is happening here. So I hope that you have some information about the simulations on these type of bodies, especially supersonic flows.